Hello fellow problem solvers, so today we're going to be doing a problem from the 2021 IMO, problem number 2. I suggest you try this problem out for a minimum of an hour, ideally 2 hours to 2.5 hours, but not more than 4.5 hours. If on the other hand you'd like to go along with us, I suggest you take a preliminary look of 30 minutes. And now the results are out from the 2021 IMO, and this is looking to be one of the hardest problems number 2 of all time. So now, without further ado, let's begin. So this is what we have to prove. We need to prove that this sum right here is less than or equal to this sum right here for all x1 through xn, which are in the real numbers. Now to me, this thing looks complicated. So what do you do when you find something complicated? And the answer is this is like a general problem solving philosophy thing that you play around with small cases and try to solve these and try to maybe get some ideas about the general case from these small cases. It also helps you get acquainted with the problem. And now, if you haven't already done so, I suggest you take 20 minutes and play around with n equals 1, 2, and 3 and get some ideas. See if you notice anything about these cases. Are there any approaches that you think might work on 1, 2, 3 that also could work on other n and more general n? And now we're going to be doing that. So for n equals 1, what do we have? We have from I is 1 to 1, from j is 1 to 1. xi minus xj, so we only have the square root of x1 minus x1 in the absolute value, and here we have the square root of the absolute value of x1 plus x1. This is 0. Square root of absolute value of 0 is less than or equal to twice x1 under the square root in the absolute value, and we have equality when x1 is 0. Okay, so now for n equals 2, what do we have? Well, we're going to have I is 1 and j is 1 and 2. So for that, we're going to have a 0. We're going to have an x1 minus x2. And then for I is 2 and j is 1 and 2, we're going to have x2 minus x1. And we're going to have another 0. And on the other side, we are going to have x1 plus x1, x1 plus x2. And we're going to have x1 plus x2 again, or x2 plus x1. And we're going to have 2x2, all under absolute values. So now the question is, how do you solve this thing right here? Are there any things that you notice about this inequality? Actually, let's make it a bit nicer. We have to prove that the square root of this is less than or equal to the square root of 2x1 plus x2 twice plus the square root of 2x2. Now the first idea might be to look at all possible cases. x1 minus, if this is 0 and this is less than 0, if this is greater than 0, if this is less than 0. Look all combinations, check out what those are so that we know what's in the absolute values, that maybe squares something and gets to some sort of solution. But the reason I wouldn't take that approach, even for n equals 2, 1 is because it's complicated, but 2 is because how are you going to generalize cases for all these numbers? It doesn't seem like a plausible strategy just now. Like, I do not see a simple way to generalize this. And that's why I'm bringing it back to the heuristic that I talked about before in this channel, which is start simply before you go into complexity. So here with this, I'm going to ask you to take 5 minutes and ask yourself, is there anything you notice about this inequality right here? Anything you notice about this side as opposed to this side, or this side as opposed to this side? And the thing I notice here is that if I add some a to x1 and x2, this side remains the same, but this side changes. And the reason I'm adding a, if I subtract a and add a to the other one, then this side will remain the same. Actually, no, this side will change, but also this side will change as well. This thing won't change, but these two will. But if I'm adding a to everything, x1 and x2, then only this side is changing. And if you think about maybe this side as a function of a, then if you look at it as like x1 through x and x2 are variables, and if this is some function of a, then if you're here, like this thing remains the same always, no matter what a you add. So you can assume that you're sort of in your worst case. And maybe there is something about your worst case that can be useful, that maybe has some property that we can use. And this is also a general idea in problem solving, so to look at your worst cases, if you can actually prove something is a worst case, then tackle that because it might give you some extra problem conditions. And now, of course, the question is, what is the worst case for a function f of a is equal to the square root of 2x1 plus, okay, let's say we're adding a halves so that we have something nice here. So we have this plus twice x1 plus x2 plus a plus the square root of 2x2 plus a. Like, when is this the smallest? And actually, to be fair, we don't really need to look at the smallest. We can just say if we can go down from 0 somewhere, if 0 is not this minimum of this function at this interval. Like, if we can move a little bit to the right or to the left and get a smaller value, then that's enough, because if this is how the function looks like, we can basically ignore this case for now. Maybe this is enough. Maybe this, just so if finding the absolute minimum is too difficult, we can just find a local minimum of this function. And now here I invite you to take 5 to 10 minutes and try to find what is the minimum of a, say for on the interval around 0, like where's the local minimum here? Is 0 the minimum? Under what cases is 0 the minimum? And what can you do with this? I invite you to play around with this for 5 to 10 minutes, because then maybe we'll be able to find a minimum that has a specific property that's cool and useful. So now with that, here's the next step. So this is how I'm thinking about solving for n equals 2. If a is less than or equal to 2x2, negative 2x2, like I'm assuming these are positive just for now. And I'm looking at, okay, so that means like we're here at the end. And if we add a little bit of something to a that doesn't change the signs, we're getting a smaller value. So it means if, I mean, say this negative 2x2 was actually here, then that means at 0 we would not have the smallest, but we would be able to move towards negative 2x2. So for this interval, from negative infinity to minus 2x2, we have the minimum. If we're not at minus 2x2, then we can get to a point closer to 2x2, not greater than it, and that we'll have a smaller value. And the reason this is smaller is because this is smaller than this smaller than this, and this is smaller than this. It's actually quite nice. So on this interval, the smallest is negative 2x2. So we know that we get a smallest value here. And now the question is, what about the next interval? What about negative 2x2 and negative x1 minus x2? So if you haven't done this already, I invite you to take 5 minutes now and try to solve this one as well. Well, here we have that a is greater than or equal to negative 2x2, and it's less than or equal to negative x1 minus x2, less than or equal to negative 2x1. And now this whole expression changes. This is still negative, minus also this, x1 minus x2, a plus 2x2. Yes, I believe this is correct. And now it's not so clear what happens when we move it by epsilon in one direction or another. It's not clear what will happen, because here we're getting minus epsilon minus x1 minus x2. Like, this is smaller than this is smaller than this. But we also have alpha plus 2x2 plus epsilon. This is greater than this. And if on the other hand we subtract this epsilon, it's again not clear. Now these two are going to be smaller. Like, this is smaller, like this is bigger than this is bigger than this, but this one will be smaller than this one. So now it's not so clear just now if this sort of subtraction or addition of some epsilon, moving it around by a bit, does it change anything? And now this seems difficult to me. So what I would do here is I would actually let me play around with an actual legit case. x1 is 1 and x2 is 3. Then I'd have x1 plus x2 over 2 is equal to what is going to be equal to 2. Or I can have this, half of this, and half of this. So that now what the function is going to look like for a is it's going to be a plus 1, a plus 2, square root of a plus 3. Like, this is my f of a now for these specific x1 and x2. And now I am stuck in the case where a is between negative 1 and negative 2. So where I have plus 1, yes, square root of a plus 1, This is the square root of 2 minus a. And no, it's minus 2 minus a, and this is the square root of... Actually, no. I'm stuck in the case between -3 and -2. So this should be -1 minus a. This should be minus 2 minus a, and this should be 3 plus a. I believe that is the case. Yes. And now I invite you to play around with this case for another 2-3 minutes. See if you can solve this, like this specific case, a between -3 and -2, and what f of a like is, where's the local minimum, and here's the solution. So this is the next idea for a between -3 and -2. Like, what are all of these functions? Well, they are just like the square root function, the absolute value of the square root function, starting at some point, and instead of starting from 0 and going like this, it starts from -1, -2, or -3. It starts from what the 0 inside this absolute value is. Now, if you think about adding them up, you see sometimes you will move towards -3, and sometimes you'll move towards -2. But it depends where you are. But the thing is, if you are between -3 and -2, you'll always be able to move at one place or the other. And here's the thing how you can prove that you can move one place or the other. And this is when you have a function where you have two minima. You're at some point. This is minimum. This is A, this is B. Forget this right now. And we're at point C. And I want to show that I can move either here or here. Like, I don't care which way I'm going to move. I care that I'm going to go either to the A or towards B. And what's the same thing as showing that? Well, it's the same thing as if I show that if I go a little bit towards A and a little bit towards B, and I take their mean, that I am below this value where C is at. So you think of it like this. A, this is your minimum, and here you have B, you're here. This is the point C. You take C plus some epsilon, C minus some epsilon, and now their mean is here. And if their mean is below C, that means one of them needs to be below C. And here, what that translates into is that we have this, like, what's their mean? The mean is A plus 3 plus epsilon plus A plus 3 minus epsilon. And this over 2 is the mean. And this is greater than or equal to A plus 3. And the reason we can do this pairwise is because this whole this square root of absolute A plus some value constant function is also like this. If you're not at -C, then you can move towards -C. So that means you can do this sort of thing right here. And this is true, and how we can actually prove this is just by, if we square, we will have A plus 3 plus epsilon, square root of A, actually now we'll have A plus 3 minus epsilon, and we will have 4 times A plus 3, and we'll have twice the square roots of these two multiplied. Now, A plus 3 plus epsilon and A plus 3 minus epsilon and A plus 3 are all of the same sign. So now, if that sign is positive, let's just do A plus 3 is equal to y. Then we have y plus epsilon. Let's assume y is greater than 0. Then y plus epsilon plus y minus epsilon, that's what this side will be, plus 2 square roots of y squared minus epsilon squared, that's what happens when you multiply these two out, needs to be less than or equal to 4 times y. Epsilons cancel out, y's cancel out, you get 2y. Divide by 2, you get y is greater than or equal to the square root of y squared minus epsilon squared for some small epsilons, for some small nudge to one of the sides. And now with this idea, I invite you to take 10 to 15 minutes and try to solve the case for n equals 2, and maybe even think about how you could potentially generalize this. Here's the next step. So we're going to prove that the local minima around 0 for f of a is for a equals negative xi minus xj for some I and j. And the way we do this is, let's assume xi plus xj isn't 0 for every single I and j. And then what do we have? We have that there's an epsilon that if we move it around a bit, it doesn't change the sign of xi plus xj. So xi plus xj plus and minus epsilon has the same sign as xi plus xj. And now we have f of plus and minus epsilon. Actually, f of epsilon plus f of negative epsilon is going to be equal to what? is going to be equal to the sum ij, the square root of xi plus xj plus epsilon plus the square root of xi plus xj minus epsilon. And now we prove that the thing we already did, that y plus epsilon plus y minus epsilon is actually less than or equal to what? 2 times the square root of y. And the way we do that is if epsilon is small enough. Y is not 0, so we can find an epsilon such that none of these change signs. And this is true because when we square it, we get this is true if and only if the absolute value of y is greater than or equal to the square root of y squared minus epsilon squared. And we know this is true, that means this is true. And this is in both cases. So now with that, we know that f of epsilon plus f of negative epsilon is less than or equal to twice f of 0. And now this implies that f of 0 is greater than or equal to f of epsilon or f of negative epsilon. It could be greater than or equal to both of them, but it's greater than or equal to at least one of them. And now what this means is that if we don't have xi plus xj is 0 for some I and j, that means we can always move towards that point where xi plus xj is 0 for some I and j. And one more thing to be 100% clear here is that the reason we want to just like keep moving on to infinity is because as f of a approaches infinity and negative infinity, this becomes infinite. This becomes bigger than any constant that you want. It's for a is equal to c squared plus the maximum of the absolute value of xi plus xj. You have that this whole thing is greater than c. So, and if a is negative c squared, you again have negative c squared plus some big constant bigger than all of these. Then we also have this thing is greater than some constant. So that's why we won't always be going down to negative, but we will find this minimum somewhere. It's going to be an actual real number. And now with that, we can, this implies for our case, xn equals 2, we have either that the minimum will be when either x1 plus x2 is 0, or when 2 times x1 is 0, or 2 times x2. Now, in the case where 2 times x1 is 0, we will have that, we'll have x2 on that side, and on this side we'll have the square root, actually we'll have twice this. Then we'll have twice x2. Oh, these two cancel out. And then we are left with also the square root of 2x2. And this is greater than or equal to 0 with equality if and only if x1 is x2 is 0. If x1 plus x2 is 0, then what we have for our 2 case is, so that's just like x2 is negative x1. That means that that side we have 2 square roots of the absolute value of 2x1. And on the other side, we have this is less than or equal to, well, we have 2 times x1 plus x2 is 0. So 2 times, so that's 0. And then we'll have 2x1. And for 2x2, we'll have the same thing. So again, we get this is 0 is greater than or equal to 0. We have an inequality. And now here I invite you to actually do the general case. Like this thing is general right now, but try to put all these arguments together into a solution for the next 10 minutes. And now here's the solution. So first we have the setup. Notice that if we change this n tuple to xi plus a over 2, the left-hand side is the same while the right-hand side is different. And so we can assume that we're solving the worst right-hand side, which is the local minimum around 0, like defined for the function defined of the right-hand side in a, which is this. And we prove that this is achieved for a equals negative xi minus xj for some I and j, not necessarily different. So we have this. And now let's assume that xi plus xj is different from 0 for all I and j. We now use the fact that y plus epsilon the square root of y plus epsilon plus the square root of y minus epsilon is less than or equal to twice the square root of y, absolute value of y, for y not equal to 0 and epsilon small enough. And this is true if and only if y minus epsilon, y squared minus epsilon squared is less than or equal to the absolute value of y, and this is true by definition. And now if xi plus xj is 0, then we have that f of epsilon plus f of negative epsilon, just summing all these up, is less than or equal to twice f of 0. And now this thing right here implies that f of 0 is going to be less than or equal to f of epsilon or f of negative epsilon. So now this implies that if xi plus xj is different from 0 for all I and j, that implies that f of 0 isn't the minimum. So now, with this in mind, we know that the minimum will be reached when one of the when xi plus xj is equal to 0 for some I and j. And now we have two cases. Case 1 is when I is equal to j, and case 2 is when I is different from j. And now let's solve these cases. So for one of the cases, we have if xi is 0, for say I equals n, without any loss of generality, we can say this. Then we get that the left-hand side is equal to this, and the right-hand side is equal to this. Now after these square roots of xi, the sum of these cancel out, then what we're left with is just the case for n equals 1 variables instead of n, which we can maybe think of inductively. And in the other case, if xi plus xj is equal to 0, say for I is equal to n and j is equal to n minus 1, like again without any loss of generality, then from here what we have is we get this, we get that the right hand side is equal to the thing for n minus 2 plus some leftovers, which mind you have xn minus 1 plus xi and xn minus 1 minus xi. And the left hand side is also similar, like we have this, the same thing that we have for n minus 2, like the actual left hand side for n minus 2, and we have these two things which are identical to this and they cancel out. So we can think of the whole proof as an inductive proof. For n equals, say, n equals 1, we have proved it because it's 0 greater than or equal to the square root of 2x1, which is always true. We can do n equals 2 and prove that, but also I think n equals 0 is a valid proof, because for n equals 2 we will just be jumping down to n equals 0 if x1 plus x2 is 0. Or we can just say, like, if x1 plus x2 is 0, then what we will have is, on one side we'll have 2 times 2x1, and on the other side we'll have 2 square roots of 2x1, and we'll be done. And now with this, we've done everything that we needed to do, except one more thing, which is we need to prove that a minimum actually exists, i.e. that this function right here, f of a, like, doesn't go into negative infinity when you get a as big as possible or as small as possible. However, we can easily show this, because if you take a to be some c, like some absolute value of plus or minus c, plus or minus the maximum of xi plus xj, or even the sum of all xi plus xj and the sum of xi minus xj over all I and j, I think if you take a to be this, then f of a is going to be greater than some or equal to this constant right here. So in any case, and if you take c to be negative, like absolute value of negative c, and I think you can subtract this, then you also get, as a goes towards negative infinity, it also becomes as positive as you want it to be. Now this thing, along with our argument beforehand, namely that we can go with 2xi is 0 for I equals n, we have our inductive case for n minus 1. And if xi plus xj is 0, then we have the inductive case for n minus 2 with n equals 1 and n equals 0, which is 0 greater than or equal to 0, which is true. with these two cases, we are done via induction, strong induction, and this solves the second problem of the IMO. And I think what's important to note here is the steps that we need to take here. We needed to first and foremost look at this whole expression that we had on both sides, xi plus xj. We need to look at this thing as a like a big picture view. You need to have like xi all the way till xn. If we add some constant a over 2 to every one of these, then this side remains the same, but this one doesn't change. And then with that, we get the idea, okay, then we can assume the worst. Like, let's assume we have the worst possible xi through xj for like this fixed differences. And it's really playing with that assumption that we have the worst possible case that leads us to the conclusion that the sum of 2 of xi for some I and j, not necessarily distinct, needs to be 0. And because that's what happens in the worst case. And the way we really get to that is seeing, like, playing around with these smaller cases. You can see that this sort of thing will happen. And that really that's playing around really epitomizes this whole sort of principle that's used again and again, which is you play around with small cases to build up a general case, like we played with n equals 2, and then we had cases like whether it's negative 2x1, negative x1 minus x2, or it's negative 2x2, where is a on this line, and where is 0? And with that, like, what happens if we move a bit to one side or the other? How can we show that we are not done? And also then thinking about graphically, just we're adding these sorts of functions together, functions of the same type, we're adding them together, and then it's a matter of us proving that once, like, what we actually figured out is once we add these functions together, we get functions with the same property. And this property is called, I think, either convexity or concavity. I'm not sure. I mean, the property that we can always move down one place or the other. Like, if we're somewhere, then if the signs haven't changed, we can go towards this minimum at one place. And this idea, along with then proving that, realizing that if a function looks like this, and if you take just a little bit of nudge to the left to right, and if you take their mean, you will be below this value that you're already on. That sort of led to a formalization that y plus epsilon plus y minus epsilon is less than or equal to twice absolute value of y. Of course, all of this under a square root. And all of this solves our problem. And it's a difficult problem, I'm not gonna lie. It has the worst results that I know of for the number of people that have solved it as a number 2 or number 5 problem. And nonetheless, I think this is a controversial opinion, but I really like this problem just because, like, there's something that you can, like, look at the graphs of these functions and think about going left or right. But it might be maybe too difficult, too foreign, too much like an undergrad competition instead of a high school competition in math. And that really solves our problem. That's our commentary. And as always, thanks for problem solving.